Hello everyone. In this session, I'd like to explain the RL circuit. In RL circuit, resistors and inductors are connected in series. So we apply the Kirchhoff's loop rule following this direction of the loop. So epsilon minus IR minus L di dt. This is the differential equations. We could solve. So this is di dt equal minus R over L I minus epsilon over R di I minus epsilon over R equal minus R over L dt integrate in the both sides log I minus epsilon over R minus R over LT plus constant I equal epsilon over R plus C sub 0 exponential minus R over LT. So C sub 0 exponential constant. Then again we apply the initial conditions. At t equals 0, current is 0. So we applied this equation to find out 0 equal epsilon over R plus C sub 0. So C sub 0 equal minus epsilon over R. Current is calculated epsilon over R 1 minus exponential minus R over LT. If we introduce the time constant of the tau equal L over R, this becomes epsilon over R 1 minus exponential minus T over tau. We have this expression for the current. So current is increasing, and finally it becomes epsilon over R. This is the RL circuit. If we remove the charge, this charge, current is decaying in a RL circuit. We don't have any terms related to epsilons. So new equations expressed here. Then differential equations becomes a di over dt equal minus R over Li log I equal minus R over Lt plus constant. I becomes I sub 0 exponential minus T over tau. So I sub 0 is the exponential constant. So we have an expression for this one. So current is decreasing. If we remove the batteries from the RL circuit, then electrical oscillation you could discover. So we apply the Kirchhoff's rules. Minus L di dt minus Q over C. Again, we considered I equal dQ over dt. Substitute. Then it becomes the second derivative. The answer expressed with a trigonometric functions, cosine or sine. In this case, I choose a cosine as a solution to this differential equations. Lower case of the q equal capital Q cosine omega t plus phi. Angular frequency of the oscillation is coming from the distance. This is a square of the oscillations. We'd like to consider the energies. So we start with the basic equations. Minus L di over dt minus Q over C equals 0. Then we multiply the I equal dQ dt. The first terms is expressed minus L I di dt. We multiply the I minus Q over C dQ dt. So this is correspond to I equals 0. We multiply this into these terms and these terms. So I is here and the dq is here. If you move the terms inside of the derivative, it becomes 1 over 2 Li squares plus 1 over 2 Q squares over C equals 0. So derivative of this quantity is 0. So this means inside of the parenthesis becomes constant quantities. So from here, 1 over 2 Li square plus 1 over 2 Q square over C is a constant quantity. This is total amount of the energy stored in a circuit, LC circuit. So when the energy is stored in the capacitance, total amount of energy. Then with the times, total energy should be constant. Some of the energy is transferred to the coil and the total energy doesn't change. So this energy is moving to the inductance. At the time, charge of the capacitor is 0 and the total into the coil. The energy is decreasing. Inductor decreased energy is transferred in the capacitance. Then is returned to this case. So this is the time series of the changing of the energies between the inductor and the capacitors. This is energy conservation in a LC circuit. This is the energy stored in the inductors as a magnetic field energies. This is the energy stored in the capacitors as the electric field energies. Then these two energy is changing, converted from the one form to the another forms, from the electric field energy to the magnetic field energy, and the magnetic field energy to the electric field energy. Sum of the magnetic field and electric field energy is constant. We could find the conservation of energies in the LC circuit. Last one is the LRC circuit. So in this case is the inductor and the capacitor and the resistor are connected in series. So we consider Kirchhoff's loop rules. So this is the equations by applying the loop rule. I equal dq over dt. You can substitute. Then it becomes a second order differential equations. Equations we need to solve is dq plus r over l dq over dt plus 1 over lc q equals 0. Then when we solve this type of the differential equations, you can substitute q equal exponential lambda t. Substitute. Then equation becomes for lambda square plus r over l lambda plus 1 over lc equals 0. Then lambda, you can solve the lambda is minus r over 2l plus minus 1 over 2 square root r over l square minus 4 over lc. So when the r square is smaller than the 4l over c, inside of the square root becomes a negative quantities. So we could express this equations becomes minus r over 2l plus minus square root 1 over lc minus r squares over 4l square times I is the imaginary numbers. So when the lambda becomes the imaginary numbers, answer is expressed with the cosine and sine trigonometric functions. If you are interested in finding the solutions, maybe it's better to take my differential equation course in futures. So answer is expressed with the cosine function or sine functions, but in this case I choose the cosine function. The charge is decreasing with times because minus RT over 12. Because this is negative quantities, magnitude of the Q is decreasing. And the cosine terms responsible for the oscillations. So charge on the capacitors is changing with times, is oscillating, but the magnitude is decreasing. This is a solution to the LRC circuit. So I explained some circuit in these lectures. Okay, this is the end of this session, and also that this is the end of today's session.